Okay, today we're looking at electrochemical cells. First of all, I've just started with a few definitions and terms, and then we'll get into representing it. So an electrochemical cell is an apparatus that uses a redox reaction to produce electrical energy, or it can use electrical energy to produce a chemical reaction. So today we're going to focus on the first part, which is using the redox reaction to produce electrical energy. And that is a voltaic cell. It takes that energy and converts it to electrical energy through spontaneous redox reactions. So before we start representing it, I'm going to use a few terms, so let's just make sure we know what they are. First of all, current is the flow of electrons. Voltage is a unit of electric potential. What is electric potential? It is the ability for your cell to do work, right? So you have this potential to do work. How much potential is measured in volts. And the electrodes are where the electrons flow in and out within the cell. And those are respectively called the anode and cathode, and we'll get into that when we represent it. So how voltaic cells work. So a few key points to keep in mind. First of all, oxidation occurs at the anode. And the nice way to always remember that is just vowels. Oxidation, anode. Put the vowels together. Okay? Reduction occurs at the cathode. Okay, so there's two electrodes, oxidation anode, reduction cathode. All right, we know oxidation is losing electrons, right? So when oxidation occurs at the anode, it releases those electrons and they travel from the anode to the cathode, right? Where reduction occurs, where those electrons are gained. All right? So at the cathode, we're gaining mass, all right? Because what is happening is as that substance is reduced, we're taking ions and converting them to solid. And so they're going to, you could say, precipitate or plate out on the cathode, as you'll see visually soon. The anode is going to lose in mass because that solid that exists is losing electrons and becoming ions in solution. All right, so the anode is going to lose in mass. And just another key point in terms of representing it visually, a salt bridge exists, and I know you have heard this before, but just to emphasize, to maintain balance. So neither solution at the anode or cathode become excessively positive or negative. And again, I'll explain that more when we represent it visually. So I've started this very simple drawing. All right, we are going to look at this, and we are going to start labeling some things on this. So first of all, this is my anode. This is my cathode. All right, I'm going to do a really common example. Let's do copper and silver. All right, so this is going to be solid copper. This is going to be solid silver. And whatever metal exists at each electrode, you have to have that same metal existing in ions in the solution. So it could be any solution as long as it contains that metal, right? A soluble solution. So we know all nitrates are soluble, so a copper nitrate, silver nitrate solution would be really good. Probably that's a great go-to. I was going to say a lot of chlorides are soluble, but not with silver. So we could say that this is a copper nitrate solution. And we could say that this is a silver nitrate solution. Right, so that means that we've got copper ions floating around in here as well as nitrate ions, right? And in here we have silver ions floating around as well as nitrate ions. All right, so whatever metal exists at each cathode has to also exist in the solution. All right, we will insert, I'm going to maybe just change colors again here, I don't know what to. Let's insert something here that will represent my salt bridge. All right, so your salt bridge, I guess it should connect actually to the solution. All right, what that is, it contains ions that are able to move back and forth. So it needs to also contain a soluble salt, all right, and a salt that won't precipitate with anything else, right? So a great soluble salt would be either a sodium nitrate or a potassium nitrate or something like that. Okay, so this salt bridge contains potassium nitrate, and I'll explain what happens with that later as we put this together. All right, so in this scenario, I'm just going to move down for a few minutes here. What we have happening is copper will be oxidized. It is going to form Cu2 positive and give away 2 electrons. All right, silver will be reduced. It is going to gain electron and form silver metal. All right, and the ratio, yes, will be 2 to 1, just because if copper's got 2 electrons to give away, we're going to need 2 silvers here, right? So the balanced reaction to represent this, we would double this, and it will be copper plus 2 Ag positive is yielding Cu2 positive plus 2 solid copper, just to balance the exchange of electrons. All right. All right, so if we connect these 2 metals with a wire, all right, that will allow copper to release its electrons as it's oxidized, send them through the wire and onto the silver. All right, and as this silver takes these electrons, it pulls the silver ions out of solution and they begin to plate on this silver cathode. All right, so that's why it gains in mass, because the silver ions are being pulled from the solution and plating on the metal. Over here where copper is being oxidized, right, we are losing solid copper and it's putting more copper ions in the solution as it becomes oxidized. So here's where you can see the potential for trouble, right? Because as copper continues to give electrons and add copper ions to the solution, this is going to become full of positive ions and become excessively positive. And over here, as the silver takes electrons and pulls ions out of the solution, it's going to leave a whole lot of nitrates and leave this solution excessively negative. So the salt bridge, right, sends the potassium ions this way to balance out the negative of the nitrates, and it sends the nitrate ions this way to balance out the positive of the copper to keep those solutions closer to neutral. All right, so we have this reaction happening, and it is a spontaneous reaction. Copper will naturally want to give its electrons to silver. We'll explain that later. And silver takes it and plates out more silver and is reduced.